No, it's been off. It's on now, but it's been off. Okay. Okay. Does this notation make sense? Okay. Now well, where the energy is basically the integral of ds dt. No. Okay. Now we proved this modulo a few statements, namely there was a lemma which we didn't prove, and there was the Ascoli theorem as well, which I did mention but didn't prove either. Okay, now does everyone remember what the Ascoli theorem is about? Теорема Арцела-Аскаля. Значит, имеет ли хоть какой-нибудь смысл? Не имеет. Okay. Well, let me briefly. It's a useful theorem. Let me briefly say something about this theorem. So we. We start with a family of functions from a compact metric space to R, and we want to know when this family is compact with respect to the uniform norm. Does the expression the uniform norm make any sense? Basically, on this space we have a natural norm given by taking the supremum of the modulus, or, which is the same, the maximum. X is compact, so the maximum is attained somewhere. Okay, well, there is another topology, the compact open topology, and in this particular case it coincides with the norm topology. If the words compact open topology do not make sense, let's forget about them and focus on the norm. Okay, we want to know when F is compact, and the answer is the family F is compact if and only if it is uniformly bounded. Well, every element of F individually is bounded. There aren't any surprises there. And uniformly bounded means there is a single constant which is greater than or equal all elements of F, or the modulus of every element of F. Okay, and what's the other condition? Does anyone remember? А по-английски? No, semi-continuous is something else. Well, I think the correct terminology is uniformly equicontinuous. We'll check it in a minute. You sure? Okay. Last time I checked, I looked it up. So if this is the same term, it's correct. What does this mean? Well, we know every function from a compact metric space to R is, or in fact to any metric space, not necessarily R, is uniformly continuous. This means for every epsilon there is a delta such that once arbitrary 2 points of X are delta close, their images are epsilon close. And uniformly equicontinuous means we're able to find the same delta which that would work for all elements of F and for all x1, x2 inside X once we are given an epsilon. Володя, значит, понятно ли, что здесь происходит? Значит, непрерывность, более сильные условия равномерной непрерывность. Вот, а здесь, значит, еще более сильные условия, значит, то же самое, но одновременно для всех элементов семейства. Okay. Okay, well, let me erase the definition of the energy. What else? Yes, what did we prove? We proved that actually if the energy is finite, then okay, let me write it slightly differently. Then both du by ds and Okay, so we proved that when s goes to plus or minus infinity, the both this part and this part tend to 0 uniformly in T. Okay, now we want to apply the Arcelor theorem. Well, let me introduce an auxiliary space of maps such that there's a problem here. I need to multiply by gt. Okay, so I want to consider the space of approximate solutions of this equation, meaning the difference is not 0, but it's less than epsilon, and y is smooth. Okay, now despite the fact that y is smooth, I want to consider this space with the submetric. Well, what does it mean? What's the submetric? Well, there are several ways to look at it. Where does this vector live? Well, it lives in the tangent space at y of t, in the tangent space to m at y of t. Well, let's assume that we have some metric on m, and we take the modulus in this metric. Now, well, it's sort of obvious that I want to apply this theorem, but am I allowed to? Let's think. Well, first of all, I want to. This theorem is not quite what we're after. Well, for one thing, the target is R, and here the target is M. Well, it doesn't really matter. We can always replace here R with Rn, and we'll get the same result. Okay, now, yes, so if we replace R with Rn, the rest will still be true, and then we can embed M in some Euclidean space, and we'll get a family of functions defined on some Euclidean space. Now, the first condition, uniformly bounded, is automatic. Why? Well, because M is compact. Well, what about the second one? Well, the second one, in general, is trickier than the first one. But as I mentioned last week, if X happens to be a smooth manifold, then one can replace this condition by requiring that all derivatives should be, and if all elements of F on top of this are C1, then uniformly equicontinuous is equivalent to, or at least follows from, the condition that all derivatives should be uniformly bounded. Okay, so this condition at least follows from requiring all the derivatives to be uniformly bounded if F is a space of C1 functions on a smooth compact manifold. Well, in our case S1, it is smooth and compact, so well, it makes sense whether or not this is true, and well, there are not too many derivatives. There's just one. The circle is one-dimensional. Okay, now well, let's look at this equation. This part is well, uniformly bounded, basically for the same reason as asking Okay, so this part is uniformly bounded for the same reason as the one for which y is uniformly bounded. This is this thing is this thing is uniformly bounded. Okay, so well, here we have y inside some compact. Y is a point of a compact manifold. Xt is a family of vector fields on this manifold, which here T also here T is the same T as here. It's an element of the circle. We have a compact a family of vector fields on a compact manifold, which is parametrized by something compact. And for similar reasons, when we take this field and multiply it by jt, we get something something bounded as well. So my claim is that this uniformly in T inside S1. Okay, now well, what remains is well, the difference is bounded. Well, it's part of the definition, so the derivatives are bounded. Now, does this argument make sense? Detia is not here, so you should be paying double attention.
Я не понял, почему правая часть ограничена. Ну, вот это JT, XT, apply.
Well, JT is something that also depends depends continuously on T inside S1. And so does XT. So basically, this whole expression JT_XT is a one periodic vector field on M. And one periodic means that it's a family of vector fields which depends on a parameter from S1. Okay, let's have a look at this again. Does it make sense? Is there any cheating involved? I don't think so, but pay attention. Okay. Okay. So we are allowed to apply the Arcelor-Ascoli theorem, and we conclude that S of epsilon is compact in the sub-topology. fixed. And we also know that by the way, here as well, I forgot to multiply by j t. Okay. Or not? No, no, no. Hold on. Hold on. No, 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 no. Sorry. No. Here we don't need to multiply. Nor do we need to multiply here. It's jt times times the whole thing. So no, and here what it says. Okay, sorry. Sorry. So basically, we want the gradient of the symplectic action, and in the equation we need to in the equation for the gradient flow we need to put j of t here and here. But when we consider this and the rest separately, there is no need to. Okay. So the subtopology. Well, let's look at this statement. What does this statement mean? Well, it means that for every epsilon, there exists I don't know how to delta. There exists a c greater than 0. Such that if S is greater than, if the modulus of S is greater than C, then U then U restricted to S belongs to this space S of epsilon. Oh, and by the way, S of 0 is precisely the set of all solutions, smooth solutions of this equation.
What do you mean by this U, S?
Well, I mean that I fix S and consider U as a function of t. So this is a rephrasement of this. Okay, now how to, and by the way, we did assume that this set is finite at some point. Basically, if it is infinite, then we don't need to prove anything, because Arnold's conjecture is about finding a lower bound for the number of elements in this set. Okay, now what do we do? Yeah, so well, also for obvious reasons, S of 0 is the intersection of all epsilon greater than 0, S of epsilon. And I want to prove that I want to prove that this thing converges to some element of this space. Let's. Well, first of all, just by taking any sequence of t's and then choosing a subsequence, we can find a convergent one, and then this convergent subsequence will converge to an element of S node, and the the rest. So what remains is to prove that U itself will converge to the same element of S naught.
Wait, to take a sequence of T's
of S's. So there is. So there exist sequences, and what I want is I want the convergence not just for a subsequence but for S going to plus or minus infinity. So, for example, what I want to avoid is U of S jumping between two solutions as S goes to, for example, plus infinity. Well, let's think. Let's think. Well, it's a simple argument, but nevertheless, let's try to figure it out. Well, we may assume that that this thing depends continuously on S as a function from R to maps from the circle to M. See if this helps. Okay, so we
Is it uniformly continuous?
well, not necessarily, but let's think a little. Well, it's not uniformly continuous, not necessarily. Well, R is not compact. Okay, so well, let me state a conjecture. We'll check it during the break. Suppose we have a family of nested subsets of a compact metric space, and the intersection. Suppose also that the intersection of all those is finite. Then for all epsilon there is an n such that for all n greater than or equal n, Bn is inside U, B epsilon, where B is the intersection.
Мы хотим, чтобы у нас, когда начинается стремиться из плюса к минус бесконечности, к одному и тому же решению.
Нет, это совершенно не обязательно, два разных решения.
Наверное, нужно переместиться в другую тоже.
Well, anyway, if let's first let's assume this conjecture for a minute. Now, my claim is that if this conjecture is true, then we have what we're after, because then for epsilon small enough, this neighborhood will be just U B epsilon will be just the disjoint union of the epsilon neighborhoods of the elements of B, and we know that when C is when the modulus of S is large enough, for example, large and positive. So, for example, S greater than C. Then U of S will be inside this disjoint union. But U of S depends continuously on S, so starting from C large enough, U of S will be inside the epsilon neighborhood of just one element of B. And the same will happen when when S will be less than minus C. Okay, we will need to vacate the premises shortly. So let's have a look at this at this argument again and see whether or not we agree that this conjecture implies what we're after.
Ну, а там внутри вот этого шарика не может там скакать?
Ну, значит, шарик имеет радиус эпсилон.
Ну и всё.
Значит, для каждого эпсилон существует такая константа c, что для всех значит, s больших какого-то c, больших того же самого c на самом деле, значит, вот это у s, значит, как функция t попадет в наше объединение таких шариков. Но на самом деле в какой-то, значит, один шарик, значит, потому что она еще зависит непрерывно от S, и, значит, значит, дальше отсюда уже, значит, следует, что вот к этому-то, к центру этого-то шарика, значит, она будет стремиться при S, стремящемся к плюс бесконечности. Вот. Значит, аналогично, значит, когда S стремится к минус бесконечности. Okay, if we are happy with this, well, let's have a look at it again. By the way, let's also remark that a finite set could be empty, but we used the compactness of all s blah 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 as epsilon to show that there is a limit, so the intersection is not empty. Well, it's one of the numerous criteria of compactness for metric spaces. There are, well, at least a dozen different versions, and most of them are useful. Well, let's not worry about trying to remember all of them, but well, we've basically just used two. Okay. Now, let's see. So I suggest we have a break, and after the break we'll try to prove or disprove this conjecture. And if we don't prove it, then we'll have to start all over again. Well, the conjecture Well, suppose we have a nested family. Well, nested means if n is less than m, Bn contains Bm. Then for all epsilon greater than 0, there exists an n such that for all n greater than n, Bn is inside U of B epsilon, where B is the intersection. By the way, I don't think we need to assume that the intersection is finite. In our case it is, but I think this the statement should be true in general. So B may or may not be finite. To prove this, let's try to remember. Do we know what the Hausdorff metric is? Okay. Now,
Sorry, B is what?
B may or may not be finite. Well, it's compact, but it may be finite or it may be not.
Can we take B is B1?
Well, B is the intersection of all the elements in the family. So. Compact non-empty. Well, there's a way to include the empty set as well, but we don't really need it.
I mean, I don't remember that. I mean, you mean by Hausdorff, you mean just 2 points can be separated, or no, you mean something different by Hausdorff?
Something different. Hausdorff. Well, every metric space is Hausdorff, but there is a separate notion, the Hausdorff metric, which is quite convenient. So let's let's recall the definition. It's the max of two things. The Well, it's the max of two things. First, we take the maximum distance from a point of A to B, and then we take the maximum distance from a point of B to A. And one can check that this is another. This is a metric, and if X is compact, so is the space of compact subsets. And if X is complete, so is the space of all compact subsets. Okay, so well, this conjecture would follow. If we manage to prove that the limit is b, the limit of bn in the house of metric is b. Now, how to prove this? Well, in our case, since we have this condition, we may as well assume X to be compact. Why? Because all those subsets are subsets of B1, and B1 is compact. Well, in fact, all of them are. So we we may assume that the space 2 to the x is compact as well. Okay, so we now have sequences in a compact space 2 to the b1. So the limit is b if and only if for every convergent subsequence the limit is b. Okay, now why is this true? Well, this is true for two reasons. Well, reason one, this limit is contained in every B and J. So it's contained in every Bn, and so it's contained in B, which is the intersection. And on the other hand, every element of B so this proves that the limit is contained in B, and on the other hand, for every element x in B, is the limit of the constant sequence x. And the constant sequence x has the property that all its terms, its jth term is in B and J. And here is one other thing we need to know about the Hausdorff metric. So suppose AN tends to A in the Hausdorff metric. Now, what is the limit in the Hausdorff metric? It's the set of all limits of the set of limits of all sequences. So xn is a sequence such that for all n, xn is inside an. Well, this is again not very difficult to prove. Start from the definition of the Hausdorff metric. So suppose we here it's important that this limit exists. So we suppose that an is a sequence inside this space such that it converges to something, and we want to describe this something. And this something is the set of all limits where xn is a sequence such that the nth term belongs to an. Well, in our case, we can take the constant sequence. So x is inside the limit b and j. So the limit of b and j contains b. So the limit is contained in b, and the limit contains b, so the limit is b. And this proves the conjecture. Does this argument make any sense?
Sorry, what do you mean by B and G convergent subsequence?
Suppose I have a compact metric space and I have a sequence. My claim is that this sequence has a limit, and moreover, this limit is equal to some element of the space, if and only if every convergent subsequence of the sequence converges to this element. And here we use the fact that we consider sequences not just somewhere, but in a compact metric space. Значит, для компактных метрических пространств мы можем сделать такой фокус. Допустим, у нас есть какая-то последовательность, кандидат на предел. Мы хотим понять, является ли этот кандидат пределом. Так вот, мы говорим, что является пределом тогда, когда все сходящиеся, вот это важно, сходящиеся подпоследовательность сходятся к этому пределу. В одну сторону это очевидно, а в другую сторону мы используем то, что из каждой последовательности можно выбрать сходящуюся подпоследовательность. So it's important here that we may view Bn as an element of the compact space to B1 C. This space is compact. I don't know. Maybe there is a shorter proof which doesn't use the Hausdorff metric, but I'm a big fan of the Hausdorff metric. So, to a man with a hammer, all the world's a nail. Okay, are there any questions, criticism, other conjectures or remarks? Okay, now let's see, so basically we've managed to prove that if the energy is finite, then the limit as s goes to plus or minus infinity of u as t is a solution of the other equation uniformly in T. Okay, now Well, the next section is moduli spaces. Do we want to say something about the moduli spaces? Значит, следующая секция Да, в следующей секции формулируется какая-то теорема, она не доказывается. Доказательство будет позже. Okay, well, the next thing we want to prove, we want to state a theorem, a big theorem about moduli spaces, and moduli spaces of what? We'll come to that in a minute. And then basically we'll need to decide whether or not we want to see the whole proof or parts of the proof, or whether or not we will just assume this theorem and move on. But first of all, let's state the theorem. Okay, so let's see. There are okay, so there are certain things which are called moduli spaces. Well, suppose we have it's not working, is it? Well, let's see. Well, this one's better. Yes, so suppose we have x plus or minus solutions of x dot minus xt of x t equals 0. Okay, and then we define m. No, it's not working either. M from x minus to x plus. And to be the space of all solutions of the equation we started with, du by dx, no, sorry, by ds, plus du by dt, and here we need to multiply by jt minus jt xt of u st equals 0. So solutions of this equation such that u such that u tends to x plus when s goes to plus infinity, and to x minus when s goes to minus infinity. Okay, and this thing is for some reason called the moduli space. Yeah, it's, none of the pens is working. The moduli space. The moduli space of what? I don't know. Just the moduli space. And now the big theorem. So the theorem is there exists a subset H reg of the set of functions of the set of functions on M, which are more precisely the set of families of one periodic families of functions on M, such that for all for all family from this H reg, the periodic solutions of this equation are non-degenerate. And for all x plus minus inside H reg, the modular space from x minus to x plus is a finite dimensional manifold. Okay, now No, there are two cohomology classes which were started, which are associated with M. One is the cohomology class of the symplectic form. Well, it is some class. But there is also the first Chern class of some complex, almost complex structure, which is compatible with the symplectic structure. And we saw that although there might be many almost complex structures compatible with omega, C1 is in fact well defined. It's a well defined class. And so this and this are just two classes inside H2 of M, and there is no reason they should be proportional. Let's require those classes to be almost proportional, or proportional in the following sense. They may not be proportional, but if we pull them back along any map from the 2-sphere to M, well, we get some cohomology classes inside H2 of the 2-sphere, which are all proportional, but we need those coefficients to be the same for all V from the sphere to M. And we've seen a few examples where tau can be explicitly calculated, and tau may be negative, positive, or even 0. And we've seen examples of all of those cases.
What is it in brackets? C1 of what?
C1 of J,
Okay.
where J is compatible with omega. So if we have this proportionality, then the dimension of M is given by the following formula. Eta of x minus, well, eta h. I'll explain what eta h is. X plus minus or plus 2 tau EU, where H is inside H reg. U is inside M x minus x plus. And what is eta? Well, eta is complicated. Let's say a few words about eta. Well, eta. Yes, eta can be defined in terms of the Conley-Zander index. Okay, so let's say a few words about that. So the question is, what is eta? Okay, now well, suppose we have a one periodic solution of this equation. And suppose U is a map from the unit disk in C to M such that it extends X. Then there is the Conley-Zehnder index. Mu mu h of x and u. And by the way, before we start talking about this thing, we would need to choose an h. Well, same as here. An h, a map from M cross the circle to R. So we have the Conley-Zehnder index mxu such that mu h x u connected some with A is mu h of x u plus is there just a plus? No, it's a minus. Minus 2 C1 of A. For all A, for all A, a map from for all maps A from the sphere to M. Okay, what is U disjoint, connected sum with A. U is a map from the disk. Well, suppose we have a map from the sphere to M that takes the center of the disk to the same element as the image of the marked point on the sphere. Then we can form the connected sum in an obvious way. Well, let's see why this connected sum is well defined. There could be what could happen is the image of the marked point may not be the same as the image of the center. So what do we do? Well, we don't really do anything. It's just we don't know what this is. But the claim is the result is this thing is not necessarily well defined as a map, but mu h is well defined. At the moment, this claim doesn't make any sense because we haven't defined it yet. So far, so good. But what is C1 of A? Well, same as here. We take any complex structure, almost complex structure compatible with omega. It has a C1. We pull it back along A. And we get something, and the something is what we call C1 of A. Well, the something lives in H2 of the sphere. We identify H2 of the sphere with R using the fundamental class. Okay, so this is completely out of the blue. We don't know why this makes sense, how to define UH, don't know anything. But, such a thing exists, or so they say. Anyway. Okay, so and recall that our purpose is to, our goal is to define eta h. Okay, well, the next step is the next step, recall that we also have AH. And moreover, AH of X A connected sum with U is AH of X U plus or is it minus? Okay, but this time we're able to figure it out because we know what AH is. Minus omega of A. Well, omega of A is the pullback the pullback of we just take the pullback of omega along A. Okay, now why do we have this? Let's recall where U participates in this construction. We basically integrate omega along U, where U is a map from the unit disk to M, and then my claim is that this thing is okay, and suppose I take a given map U from the disk to M and connect it summit with a sum map A from S2 to M. There are several ways to connect and sum those two maps, and for example, we can join if the base points don't match, we can join them using this path or that path, but the integral of omega does not change. So this thing is well defined. Well, basically, the integration along a path contributes 0, and this thing is well defined. Okay, now we want to define eta. We want to define eta, and okay, eta. Now we take eta to be eta h. We take it to be mu h. So eta e. It only depends on a periodic solution. So eta e of x. Let's eta e of x is mu h. Is it x? XU minus 2 tau AH XU. Okay, we know we know this, but what is U? U U is an arbitrary map that extends X. And basically, using this identity, we see that both contributions the result does not in fact depend on U, Why? Well, because connected summing with A gives with a map from the sphere to M gives two contributions, but those cancel. So eta may look like it depends on U, but it doesn't. The contributions cancel. То есть все такие U можно получить из любого фиксированного U, связанные суммы с элементами, с отображениями сферы. Значит, но теперь значит, мы смотрим, как вот это и вот это меняются при связанной сумме. Они меняются почти одинаковым образом. Поэтому, когда мы берем сумму с коэффициентами, значит, вклад от... То есть, значит, вот эти вот две поправки, они, значит, они убивают друг друга. Well, let's see if there's anything else we need to say about this. And okay. 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 Well, there's one other thing we probably need to mention. Well, there's an exercise. Well, let me mention an exercise, but I didn't do this exercise. So if you know how to do this exercise, please tell us. Okay. Well, we sort of stated the theorem. We know what. Well, at least we understand all the symbols. We know what this is. We sort of know what this is, sort of, because we don't know the definition of mu h. Well, never mind that. But let's imagine we do. Then we know all ingredients in this in this theorem. Oh, by the way, there is well, there is a subset, but there's one other thing I forgot to say about this subset. This subset is this subset is, well, for all we know, this subset could be empty, in which case the proof is very easy. But no, this subset is a bare subset, meaning it's a countable intersection of dense open subsets. So it's definitely non-empty. Okay, well, let me state an exercise, and then we'll probably need to finish. So there's Okay, so suppose I have suppose U suppose again I have U, a solution of the gradient flow equation, and I suppose then when x goes to when s goes to plus or minus infinity, the limit is x plus minus, and then we also assume that the energy, not the energy, well, we assume that the partial derivative with respect to s satisfies one of the equivalent conditions from last week. Then the energy of U is AH x minus U minus AH x plus U plus, where okay, where basically you, well, which one of them is arbitrary and the other one is not. U minus is arbitrary, and U plus is U minus connected some with U. Arbitrary, but arbitrary meaning arbitrary, but an arbitrary map extending x minus, and then we connected some with U, and but this time connected some. This time connected summing. The connected sum is taken in a slightly different sense, meaning we have so U gives us a map basically from the cylinder to M. Then suppose I already have U minus which extends x minus, meaning the restriction to the bottom part of the cylinder, and then the connected sum is just basically the union. So the whole thing is the connected sum. Okay. This is the connected sum, U minus connected sum with U. Okay. Now, well, I don't know how to do this exercise, but let's assume this.
What is the statement?
Well, the statement is the energy of U is this. Well, assuming this statement, there is another way to rewrite this expression, meaning, well, suppose I take eta of x minus eta of x plus. Using this definition, what do I get? I get mu minus 2 tau A okay, let's rewrite this, assuming this. This thing is mu x minus mu x minus u minus 2 tau AH x minus u. Okay, no, let me take here u minus an arbitrary map that extends x minus. Okay, now now here I take minus mu x plus u minus connected sum with u plus 2 tau AH x minus connected sum with u plus 2 tau energy of u. Okay. Okay. Now this thing 2 tau plus 2 tau is 0 by this formula, because well, this minus this is this. So we get this thing cancels with these two, and we get mu of x minus u minus mu of x plus u minus connected sum with u. So in other words, we express this this dimension in terms of the Conley Zehnder index mu h, which is great news. But we don't know what the condensate index is, so at the moment this formula doesn't make anything any better. And we don't know how to prove this. Well, at least I don't know. Okay, are there any questions? Okay, well then this is it for today, and we need to accelerate, or else we won't be able to do much during the rest of the term. We'll think about a plan.